Hey everybody, welcome to our next installment on climate change. This time we're going to look at climate science and science more broadly to understand how science is a process that is repeating through time. It's iterative, and it's always seeking a better understanding of how the world works. Would it surprise you to learn that climate change used to be a bipartisan issue? There was a time when both Democrats and Republicans were ready to work together under the leadership of George Herbert Walker Bush to pass legislation to address the climate change problem. Unfortunately, that progress came to a screeching halt, and very little has been done to address the problem over the past 40 years. This is due to a widespread and well-funded and very successful campaign to debunk climate science. It's a campaign sponsored by those who have amassed great fortunes through the production and sale of fossil fuels. Now, this may sound like conspiracy theory, but it is exceptionally well documented in the media. Check out the article written by reporter Amy Westervelt that I've assigned as part of this class. In this class, we're going to tackle some of the misinformation that has been spread about climate change science. This will involve us looking at how science is produced and what checks and controls there are to ensure its quality. But let's also acknowledge that given the importance of what climate scientists and others are saying, we should ensure that we understand the process that is creating this science. Now, the readings and videos you will do for this class will take you through this process by which science is conceived, funded, produced, and published. In this mini lecture, we'll explore several aspects of this. Now, one of the common tactics of climate change deniers and skeptics is to offer alternative explanations for why the climate is changing. Their argument is that if phenomena beyond our control, such as changes in the sun's energy output, are causing climate change, then there's no reason for us to stop burning fossil fuels such as coal, oil, gas, and to also stop things like deforestation. Here's a list of those explanations, including a mnemonic that I created to help us remember them. I'll let Dr. Hayhoe and the National Academies of Sciences present the reasons why none of these really explain the rapid rate of global warming that we're experiencing now. But let's consider the broader question. Is it wrong to challenge prevailing scientific understanding with alternative explanations? Absolutely not. Any good scientist would argue that scientific findings should be challenged when new information or ideas are made available. Continually challenging and established ideas is what makes science stronger every day. Science is a process by which we seek an ever better understanding of how the universe works. That process is rarely a forward, unerring path. Often it is messy. Progress can be sideways in our pursuit of truth. The unofficial BSc motto of forward ever, backwards never, and sideways sometimes seems very relevant here. A key insight into science is that it is an iterative process, one that repeats itself, in this case, in order to achieve a better understanding of some phenomenon. So back to the question, is it wrong to challenge climate science with alternate explanations? It's not. But, and this is a big but, when there is scientific conclusion, for example, that the climate is changing rapidly due to human actions, and that conclusion has tremendous bearing on humanity, and that conclusion is well supported with many scientific studies from multiple scientific disciplines, then it's irresponsible to throw doubt on that science unless you have very strong scientific evidence to support your view. Further, one could argue that it is immoral to sow seeds of doubt in the public on important science such as climate change and things like vaccinations when the collective fate of humanity hangs in the balance. Let's take a look at what it's like when scientists challenge existing scientific conclusions by exploring one of the things we learned about recent geologic and evolutionary history. Do you remember this quote up at the top of the slide? This is from the book that I'm working on. And that is that the last time carbon dioxide levels were over 400 parts per million was the Pliocene about 3 to 5 million years ago. And during that time, Earth was 4 to 7 degrees Fahrenheit warmer than during the pre-industrial age, and sea level has been estimated to be 72 to 82 feet higher than it is now during that time. Okay, so in that quote, of course, that's not from my own research. That's from me reading the research of others, and you see that I've got the annotations there indicating that. And one of the sources that I cited is this paper that you see cited in the middle here by Miller et al. That was published in 2012, entitled "High Tide of the Warm Pliocene: Implications of Global Sea Level for Antarctic Deglaciation." It was published in a journal called Geology in volume 40, number 5. And this is, of course, what's called a DOI. It's the permanent link to where that article is permanently stored on the web. So I've clicked over to my PDF copy of this paper that I read, the one that I was talking about here. And I want you to notice a few things about this. This is straight from the journal. Up here we have the title. And next, below the title, we see the authors. And below the authors, it lists what institutions that they work for or worked for when they did this research. So if you wanted to, you could actually reach out to these scientists and ask them questions about their science. And sometimes I do that from time to time when I've got a question about something in the research papers or I'm looking for more resources. And that's something that's commonly done by scientists to other scientists all the time. And that's all part of the accountability of the science. Being able to justify and stand by your research findings means that you need to be able to be there to answer questions about them. Now, other things I want to show you is that a journal article like this is really not written for the overall public. For example, let's take a look at this abstract, which is a summary of the research paper. Some of you in other fields are familiar with abstracts. It's a dense summary of a particular research paper. And if you just look at the first lines here, we obtained global sea level eustatic estimates with a peak of approximately 22 meters higher than present for the Pleistocene or Pliocene interval 2.7 to 3.2 million years ago from backstripping in Virginia, New Zealand, and Inuwatak Atoll in the North Pacific Ocean, benthic foraminiferal delta 18O values, and magnesium calcium delta 18O value or estimates. Folks, I don't fully understand what's going on there. The point of this is to say that researchers are writing these journal articles for other researchers in their fields. They are not doing this to communicate to the overall general public. That's what science writers do at magazines and in the press. They will take articles like this and translate them into language that you and I can more easily understand. Now, one thing scientists have to do in journal articles like this is that they have to relate their science to previous work. And you see that if you were to read these first and second paragraphs, that they're talking about their subject matter and summarizing all the work that's been done previously. It's not enough to just measure a bunch of stuff and then publish it without putting it in context. That would be ignoring a lot of important information and an important work that's been done previously. Now, the next thing I want to point out is that further along in this journal article, and you can see that it's very dense with lots of data, that they've got, let's see, I went past it here. They've got a summary in here of their methodology. Scientists need to be able to explain how they came about getting the data that they got during their study so that other scientists could potentially replicate that study and see if they also get the same thing. Replicability is a measure of quality in science. If your data are not replicable, then that calls into question whether or not your data are really showing us how the universe works. A couple other things that I want to show you in this journal article is back here at the very end. You've got the references cited. Usually it's very lengthy because authors are responsible for relating their science to all the work that is relevant that's been done before. And sometimes that can be an excruciatingly hard task, but the process is very important for helping to move science forward and seeing how the new information, the new data fit into the context of what's been done before. Okay, back up to the top of this paper again. So we've got this journal article. It took several years, maybe many years, for this research to be conducted, and many months in order to get it ready for publication. And then there's the whole publication process. It's a big, lengthy process, but now it's published, it's online, people can read it around the world. Does this mean that everything that they say here is perfectly accurate? No, not at all. This is a presentation of a hypothesis or a guess about something, and the presentation and interpretation of data that shed light on that hypothesis. That's what all this is about. This is what you've been practicing in the lab portion of this course. Could the conclusions they present in this paper be challenged based on a criticism of their interpretation? Yes, of course. What about future studies that found different data or found different conclusions? Could those challenge the conclusions of these authors? Absolutely. That's how science works. It's this iterative, critical analysis of hypotheses, data, and conclusions that brings science as a whole ever closer to a true understanding of how the world works. So I want to show you an example of how science is revised as new ideas come to light, as new information, new data are presented. So do you remember a few weeks ago when we talked about geologic history and evolutionary history, we talked about the Pleistocene, the ice ages, that time period from about 2.5 million years ago to 10,000 years ago. And we talked about the megafauna, the large mammals that were found widespread over the continents of the Earth. We talked about what the prevailing ideas are about why those species disappeared. Why don't we have mammoths and mastodons and some of the other large animals that were around? Well, what I said at the time, that it was mostly due to overhunting by the early humans that moved out across and spread out from Africa around the world. And also said that climate change played a role, but probably not a major role, because these species had all survived a lot of climate change, warming and cooling in earlier parts of the Pleistocene ice ages. But as it turns out, there's another idea that is causing us to rethink some part of that story that I presented in lecture. And that's represented here by this screenshot of a magazine article about a study that came out challenging the mechanisms by which these species went extinct. So this is a slide you've seen before. This is showing time on the x-axis, and it's ranging from the current time period over here on the right to about 17,000 years ago or so. So this section here from about 10,000 years ago to the right, this would be the Holocene. And you'll notice that on the y-axis we've got temperature, and this was temperature as measured based on ice cores in England. In Greenland. And what we see here is that as I talked about in the previous presentation, during the Holocene, temperatures were relatively stable. See how that line, it varies up and down a lot, but it's relatively stable compared to the time period before, where there was a lot of instability. And of course, this time period before, this is the tail end of the Pleistocene, which is on the left side of this graph. Now this part I have a red circle around on the graph is indicating a particularly cold time period here known as the Younger Dryas. And that was a very rapid cooling in the Earth's climate just before the Holocene. Prior to this time period, the Earth was warming, as you see the gradual change of temperature ever going upwards. And you can see how that line leads up to where the Holocene is now. But it's during this time period right here that things got exceptionally cold. And geologists have been puzzling over that for quite some time as to what could have caused that. And that has implications for evolution because we lost a lot of large megafauna during that time period as well. Okay, so what is this new idea that's being presented about what could have caused the extinction of the megafauna and contributed to that cooling that we saw during the Younger Dryas? What you see here on this slide is an excerpt from a journal article, not a journal article, but a magazine article from a magazine called SciTech Daily. And they find interesting scientific journal articles and then write popular articles about them for the public to read and enjoy. And what you see here is that, and I've highlighted in yellow the key elements of this, is that the new idea suggests that that in fact it was one of the things contributing to the cooling was another impact of a meteor or small comet with Earth about the time at the beginning of the Younger Dryas. And it tells you a little bit about how scientists are coming to this conclusion. It's based on taking cores from some ponds, and in this case in South Carolina, but this has also been done in other areas of the Earth, including Asia and Europe and other parts of North America, South America, Africa is mentioned, and Chile. And finding a layer of platinum, which is an element that is more common in asteroids and very rare on Earth. And it's found in the sediments of these lakes and other places where these sediments accumulated at the time. And we've already talked about how water bodies, everything from lakes to large oceans, accumulate eroded sediments in layers, and how those layers can be dated using different means, and how by examining the composition of those layers, we can tell something about what Earth's environment was like at the time. So finding these platinum spikes around the world all at about the same time suggests that there was some sort of cosmic impact. So some large structure, asteroid or comet striking the Earth during that time period. And what they're speculating here is that that impact was important for triggering the beginning of the Younger Dryas. Specifically, it was the Younger Dryas has already been linked to the idea that there was a large body of cold ice and water at the north part of the planet, and it was being held back by a large glacial ice dam, and that the rupturing of that dam allowed a lot of very cold water to go into the North Atlantic, which disrupted ocean circulation and caused the Earth to plunge into a cold climate, as they say here. And the new findings, as represented by this new study, suggest that that it might have been that impact that was the trigger for the meltwater pulse into the oceans. Okay. They're not saying that the impact was the cause of the extinction of the megafauna, but instead saying that this would have been something that is likely to have contributed to and maybe been the trigger for the events leading to major climate change on the planet, very sudden, very rapid climate change on the planet, and causing the extinction of many, many species. Now, do we know for sure that this new view is the way that things went down? Absolutely not. A lot of work is going to have to be done by geologists in order to find more evidence to support this, and especially finding other lines of evidence that could support this. For example, finding the impact site where this asteroid hit would be pretty important, because then if that could be dated to this time, that would be the proverbial smoking gun in terms of the evidence for this. But that's how science works. It's a collaborative effort amongst scientists of the world to try to get closer and closer to a truthful understanding of how the world works. Now, one of the things that this might illustrate you is that science is never ever fully certain about anything. You can take something like, will the sun come up tomorrow? Well, Maybe not. Maybe we, or maybe just me, maybe I live in an elaborate simulation and the programmers will kill the sun tonight while I'm sleeping. Or maybe the Earth gets obliterated by a comet tonight and there won't be a tomorrow. You never know. But maybe for reasons not yet discovered, the sun will go from its stable state now to a massive explosion this afternoon. You just never know. But what's important here is that when we've exhausted all known possible alternate explanations for something, and we can't find strong evidence or reasonable doubt for our contemporary view of things, then a hypothesis gets promoted to the level of what we call a theory. And you've seen this before. We've talked about this before with regard to evolutionary theory. And it's at that point that science moves forward, assuming that the theory is more or less true. But even then, it's important to realize that because this is science, even theories can be modified, and sometimes even fully abandoned as new discoveries arise. Okay, so that's all I wanted to cover with this presentation. Let's go over the learning objectives from this to make sure that you understand the key points I want you to get from this. First of all, that the science of climate change has been politicized. That's why we're having such strident arguments about that in the US these days. Secondly, there's been widespread misunderstanding of what science is and how it's done. And some of that misunderstanding has been spread deliberately. Third, science is an iterative process, ever seeking better understanding of how things work in the world. Fourth, scientific findings and even theories can be challenged and sometimes overturned. And finally, there are checks and controls in place to ensure that science is done properly and without bias. All right, that's a wrap.